I'm very happy to introduce the next speaker. It's Stefan Weigert from the University of York. We're very happy to have you, and he's talking about the quantum theory with non-collapsing measurements. Stefan, the floor is yours.
Thank you, Philipp, and thank you to the other Philipp for putting this together in this wonderful place and having arranged for a variety of weathers available. We'll see what tomorrow brings. Today seems to be a good day. Before coming here, I checked the weather forecast sort of last Saturday, and it said it would be raining every day, at least on my weather station, but I should have probably picked another one. Anyway, I'd like to present you some work, which is joint work with Vincenzo Fiorentino, a PhD student at York. I'm a physicist. I work in a maths department. So you will see no rigorous maths, but just some ideas. And I try to, since we have a rather mixed audience, I try to cut down on anything formal and mathematical. I'll try to focus on the main ideas. Let's maybe look at the first slide. I'll try to get the main message across in the first two slides, and then you will see a traditional outline of what this talk is going to be. But I want to walk you away with this fundamental idea, which I want to introduce now. The idea is, I want to explain to you what passive quantum theory is. And this is a new version of quantum mechanics, which has some interesting features. It gives you a lot of opportunities to think about ordinary quantum mechanics. And for reference, I have introduced the one set of standard postulates. The simplest version I could think of was to have just pure states to begin with, no density matrices. We'll come to that later. States are simply rays in some Hilbert space. Observables are self-adjoint operators. Time evolution is just unitary. Composition of system happens with the standard tensor product. And then in addition to those four postulates, I have a third one, which tells me what happens when measurements are performed in this setting. And these are the standard assumptions which we make in one version of quantum mechanics, which we might want to call the Copenhagen version, where we do have a collapse postulate. And this postulate, the measurement, refers to the measurement of M. What happens if I measure an observable M in this system in a particular state psi? The measurement postulate tells me three things. It tells me about the possible outcomes of the measurement. They are given by the eigenvalues of the observable which I'm looking at, standard textbook quantum mechanics. I have a rule, Born's rule, which tells me what the probability is to obtain these specific outcomes given a state of a system. And the third element is the update rule, which tells me what the state is after the measurement has been performed and the outcome M has been obtained. And here's the update rule in words. If I measure M and little m occurs, then the state I started out with goes to another state, namely the eigenstate of the observable M I'm looking at, associated with the outcome I found. Okay? This is the standard way. So here's a box which summarizes this in a slightly more formal way, which you all have seen before. Okay. Now, this is the setting I'm looking at. And let's have a look at textbook quantum theory modified in a simple version. I will not touch the states. I'll use the same state space as before. I will not touch the observables. I leave the observables as they are. I will assume there's a time evolution as an ordinary textbook quantum mechanics with a unitary U. Composition of systems happens as before. Now, I will make some minor change to the measurement postulate. I will actually keep the fact that the possible outcomes of the measurement are the eigenvalues of the observed, of the measured observable. The Born rule will persist. It tells me how likely the outcomes are. But, so there's one last thing I'm able to change on this slide in order to get away from quantum mechanics, and that's the update rule. So I'm going to touch the update rule and modify the update rule by modifying what we had before. Originally, we had if M occurs, then psi goes to the eigenstate of the measured observable. Now, we just relax and think about other possibilities. Could there be other update rules, right? In principle, yes, of course, there could be many. And I'll tell you about a first update rule. And that is now my passive quantum theory, which has, as explained, the first axioms up to the Born rule identical to the ones of standard quantum mechanics. But we assume if we perform this measurement on psi of M, the state actually goes to itself. So it doesn't change, right? Logically, these axioms are independent of each other. I can make this assumption here. I get a new theory, which I call passive theory because the measurements are passive. They don't impact on the state. There's no collapse. This is a non-collapsing measurement. But I retain these two interesting features from quantum mechanics, namely this probabilistic random aspect and the selection of specific possible values as outcomes. And so my measurement in PQT, passive quantum theory, is like this. I go from a normalized state, as I did before, to another normalized state, which happens to be the same I started out with. And now you can ask, okay, this is completely silly. It is, of course, silly, but that's the idea behind it. I want to do something silly in order to understand what the quantum mechanical projection postulate is responsible for in quantum theory. I have changed here the postulate which regulates the state update. So and that's the only thing, any change which I will see in this theory, in passive quantum theory, is down to the change of the update rule, and therefore is down to the modification of the projection postulate, right? A first interesting feature of this theory is that it actually only has one time evolution. You know, in the measurement problem, we face the difficulty that we have the unitary time evolution of states, and at some unspecified moments of time when we perform measurements, we have another time evolution, namely the ordinary update rule, the projection postulate kicks in. During that period, the unitary time evolution is not relevant, so I have these two competing time evolutions, which create a lot of hassle. Okay, so now you know what passive quantum theory is, and you are, of course, extremely curious to know what its properties are in order to see what the impact of the projection postulate is in ordinary quantum mechanics. So here's the outline of what I'm going to talk about. I'll embed passive quantum theory in a wider context of what is known as foil theories. I'll then have a bigger section where properties of this theory are being explored. And here's the section which contains the interesting stuff, what we learned from passive quantum theory about quantum theory, because we have fiddled with the update rule a little bit. And then there's a natural way to actually enlarge this idea, expand on it, by imagining even other update rules, because I have picked one which is probably about the simplest one you can imagine. Okay, are there any questions up to this point? Anything not clear? Because you have to have imprinted in your mind now, yeah?
One immediate thing is that what if you perform the same measurement twice?
We'll come to that, yeah. That's what we are going to explore, yeah. You had?
Yeah. How do we decide, because the state does evolve unit revolution if the system is subject to some Hamiltonian. How do we decide if the state is going to undergo a unit revolution or the update rule that was mentioned in the previous?
Well, I just take the measurement as a primitive, and the state can actually evolve as it likes all the time. When I perform a measurement, in addition, as it doesn't change the state, I just extract some information, and this unitary time evolution just continues as it did before. It doesn't create any sort of tangle, I think. Okay. Yeah, the landscape I'm in here is the landscape of foil theories of quantum theory, which you, of course, know. Foil theories have been introduced for a lot of the postulates we have. We can change the state space relative to ordinary quantum mechanics by looking at GPTs, for example. We have Specken's toy model. We have models where we have epistemic restrictions on certain sets of states we start out with. And all these investigations lead to some insights, typically about what quantum mechanics is about and what is characteristic for quantum mechanics, ideally. We can also change the observables. When we go to GPTs, we talk about effects of a certain type. It's not all observables you can think of. In an ordinary system, you restrict the set of measurements possible. There are these famous polygon models. There's another example where people look at so-called PT symmetric systems. And in those systems, people assume that the Hamiltonian, the main ingredient responsible for the time evolution of your system, is no longer a Hermitian operator, but it has some other symmetry, which still allows it, in some cases, to have real eigenvalues to get something interesting to compare with. Time evolution has, of course, been attempted to undergo change. People tried to introduce nonlinear dynamics, replacing the unitary dynamics we normally have, without much success, because you easily get phenomena which are not very desirable. In the framework of GPTs, you can also change the composition of systems by looking at different types of tensor products. I have kept the ordinary tensor product here. You can also change parts of the measurement postulate. You can try to work with different Born rules. That seems to be very hard to come up with anything as a competitor. You can actually remove the entire projection postulate in various ways by either going to a unitary version of quantum theory, like which then borders on an interpretation, like many worlds, or you use the GRW, Girardi-Rimini-Weber approach to have built-in collapses, which do the work which you need to have outcomes of measurements.
Could you just expand 2 or 3 sentences on modified Born rule? I've never seen anyone attempt to modify.
Yeah, well, I don't remember the references, but I think I can probably dig them out. Yeah. You can just, well, it normally comes in the form of people trying to derive the Born rule by saying we don't have it in the beginning, and then you might end up with, depending on your constraints, with something which is not the Born rule, and then you try to work it out whether it works or, and it doesn't. So, yeah, but there are people who have looked into this. Okay, so my motivation is down here. Passive quantum theory as I explained, is a tool to investigate the role of the projection postulate in ordinary quantum mechanics. And therefore, it is in fact a foil theory, because it's a theory which is different from quantum mechanics, but rather nearby, right? I don't do very abstract stuff here. I have the standard Hilbert space. I have everything as normal, but I change just the one single thing. And it has unitary dynamics only, as I emphasized. But I don't aim at resolving the measurement problem in any way. That's not the goal, and this theory doesn't contribute much to that. And in fact, I don't think of it as an interpretation of quantum mechanics. It's another theory which simply has another update rule. So it will have interesting implications for the interpretation of ordinary quantum mechanics, as you will see in a moment. Okay, so let's first investigate a few properties of passive quantum systems, single systems only, so no composite systems yet. We have a large bunch of information up here where PQT simply coincides with quantum theory because of the mathematical structure being identical in both theories. We have spectra of operators, we have eigenvalues and eigenstates. This is the Hilbert space setting of observables and states in the appropriate state space. We do have a unitary time evolution. We do have a no cloning theorem, for example, which only requires, which doesn't require measurements in any way. So you have just a restriction on the possible dynamics. That's what the no cloning theorem says. We have things like Gleason's theorem, Wegener's theorem. It's all there because we haven't touched the Hilbert space structure of the theory. Okay, and now let's start slowly and assume that we do not look at post-measurement states after we have done a measurement in PQT. So we discard whatever we get out of a measurement after having performed a measurement in PQT. Well, no big surprise, everything is going to be as in quantum mechanics. That's what it says here, because I never look at the post-measurement state after a measurement, so I will never see that I'm actually working with PQT instead of quantum theory. And this means I can discard the post-measurement states, and I will simply use now ensembles of systems prepared in exactly the same state all over again, as I do in ordinary quantum mechanics when I determine expectation values of operators, for example. I know I extract the eigenvalues probabilistically via the Born rule, which means that the outcomes are indistinguishable from what you would get from this ensemble approach, from what you would get in ordinary quantum mechanics. And that means, of course, that expectation values of operators in this ensemble approach will be identical to those which you get from quantum mechanics. You will get so-called preparational uncertainty relations, like Heisenberg's uncertainty relations. You will be able to do state reconstruction by measuring on a complete set in a state psi, you measure on a complete set, informationally complete set of observables. On the members of the ensemble, you get a number of expectation values which you can invert to find the state which is associated with this ensemble. So all this works if you don't look at the post-measurement state. And now we come to the interesting bit where we actually involve the post-measurement state in our reasonings. The first important feature is, and this is, in fact, it's relatively straightforward to see, as you will notice, but it is of fundamental importance because we have what we call single copy state reconstruction. So it's the same idea as state reconstruction. You measure a set, an informationally complete set of observables, Mn, whatever, depending on your Hilbert space dimensions, how many you need. The expectation values will allow you to extract the state, but in this case, you don't need an ensemble, right? Because you can recycle your state. You get the same state out of every measurement you perform, and you can just reuse it again and again, And that means that effectively these, I call them P states, are observable quantities. If someone gives you a P state in this theory, you just can work with it as an entity sitting there. You extract all the information about expectation values you need, and you identify the guy sitting there. This is effectively the conceptually most important consequence you've got in PQT.
Shouldn't that contradict your statement of a no-cloning theory? I just determine the state psi, I make two of them.
Yes, you can, but you can also do cloning in...
So you're saying no unitary cloning?
Yes,
I could clone
yes, of course. That's on the next slide.
I'm sorry.
That's okay. Thinking ahead. The unitary no-cloning theorem continues to exist. You can't find a unitary evolution which copies a given state on a blank state. But, of course, using this method, you can produce a copy of a given state. That's perfectly correct. So that, effectively, you can also do in ordinary quantum mechanics if you have an ensemble. But here, for this type of state of single copy state reconstruction, you need only a single copy. And that is quite powerful. Okay, let's continue and have a look at a few other properties. I will not go into the mathematical detail, as I said. The first item is Chris' favorite up here. We can clone unknown P states by performing a repeated measurement. We can, in fact, discriminate P states. So, given a single copy of two different states, I hand over to you one of those. You can find out which one it is with certainty, under ideal conditions, of course. And now, if I lift this up into an interpretational issue, it turns out that the wave function, in quotation marks, the state psi, is a completely ordinary, classical, real thing. It just sits there in your laboratory and you can work with it and find out which it is, etc. That's interesting in itself, that this minor change in the update rule determines the ontology of the object which you have in here for this set for these states. And now another consequence following quickly is that proper mixtures actually aren't important or relevant in passive quantum theory, because what is a proper mixture? I send you either this state with a certain probability or that state with a certain probability. If you perform measurements on the thing you received, you know which one it is. You never, in principle, need to talk about a proper mixture of these states. You can always check what you've got. It might still be okay and useful in some circumstances, if you don't look at what you get, to use the mathematical concept of a mixture, but it's not a fundamental property. Okay, and now we come to Johannes' point. What do we lose? We lose deterministic repeatability in the sense that we know in a quantum system, if we perform the same measurement twice in quick succession, we do get the same eigenvalues out because of the collapse. And if we don't allow the state to move away after the first measurement, so we measure quickly enough after the first one, we know for sure that we will get out the same eigenvalue again. That's not true here. We do get what we like to call probabilistic repeatability, because you can reproduce by this type of measurements the probability distributions with certainty which are associated with that state when you perform this particular measurement of the observable M. Okay, another rather unpleasant property, I think, is that we are no longer able to think of this duality between measurements and state preparation, because we can't force a state by a measurement into a particular state. But of course, we can reconstruct a state given a copy of a single unknown state, but then we can of course perform a unitary transformation, assuming that we can do all those, in order to prepare a desired state. So we have to go through some hoops in order to get there, but the direct link between measurements and state preparation is gone. Okay, and now comes an interesting feature, which maybe Heisenberg should have known at the time he wrote his famous paper. The preparational uncertainty relations actually still come from a single copy. I can perform measurements of two non-commuting observables on this state and create my expectation values, which I need for the variances. And they will satisfy Heisenberg's uncertainty relation. Okay? In spite of the measurement not impacting on the actual state. And this was the idea which Heisenberg had in his original paper, that a state change would actually cause the complementary variable to acquire other values, because you just fiddle around with that small electron, you give it a kick, and it just goes somewhere else. This classical thinking nowadays isn't accepted anymore, but it's quite interesting to see that you have a complete separation from of the existence of uncertainty relations from the state update rule and the collapse or the projection. They have nothing to do with each other, right? That's a quite nice and clear feature. Okay, now let's look at composite systems, because they are quite interesting as well. Suppose we now have a composite passive quantum system and a state capital psi, and we measure some observables which are defined on the entire system or on a subsystem. And then we know we can perform measurements of local observables, and we do get probabilities for M by forming this expression here as in ordinary quantum mechanics. If the other party measures N, she gets this expression here, that's another probability. But since we say that there's no projection, no collapse, these measurement results will not be correlated whatsoever, because the state before any party measuring and after any party having measured will be the same. So no cross factor correlations can exist. Interestingly, however, I can still extract probabilities for the joint occurrence of M and N, as I can also do in quantum mechanics. But these quantities here are exactly the same quantities you do get for which you need in order to violate Bell inequalities. So you can extract from this system, in spite of not having any correlations, you can, by global measurements, extract the right expressions which produce a violation of the Bell inequality. But then, interestingly, you can't use this violation to draw a conclusion that no local hidden variables can exist. So that's a rather subtle point. And the other way to express this result is that the conditional probabilities PMN are inaccessible. The theory is not locally tomographic. I can't use local measurements in order to extract information about the global state. Okay, next, here's a little summary of the main differences. So we have seen some of those. There are various things you can't do because you don't have the collapse, and this is what we were after. We want to know and see explicitly that, for example, we can actually only do local tomography because of the standard collapse postulate, which we use in quantum theory. We cannot do things like teleportation because that requires a state. I perform a measurement here and somewhere else something has to happen. I can't do quantum cryptography in specific ways. I can't steer a quantum state at a remote place to somewhere else. I can't obtain Bell violations by performing local measurements. But interestingly, passive quantum theory provides us with some advantages as well. So it's not that we only get a weaker theory, but in some respect it's also stronger. So this single copy state reconstruction is a nice example. We don't need an ensemble to determine a state, but a single copy. I mentioned single copy state discrimination. And now here's an interesting thing. You can actually improve quantum algorithms beyond recognition, because you just take a standard quantum algorithm, which calls an oracle, and then you use this phrase that sending in a superposition makes this function, which it evaluates on all the states simultaneously. And then normally in quantum mechanics, you have to do some push-ups and massaging in order to get the information out which you want. And sometimes you have to repeatedly call the oracle or do some post-oracle call transformations, etc. But if you take any of these algorithms, all you do is you run it once, including a possible call to an oracle, be it Grover or Shaw. And then you end up with a final state, which you can reconstruct from single copy reconstruction. So basically all your quantum algorithms work with a single shot, right? And that's, of course, paradise, if you think about it. And another interesting feature is you can actually simulate quantum theory using passive quantum theory, if you allow me a little time delay between the measurement and what happened, the state which you get after the measurement. Because we discussed this before, I have a box and there's one of these passive systems inside. I have a little helper in that box and I measure some observable. I get out the value m. And the only thing which differs here is that my post-measurement state is not the right one because it's the same as the one I put in. But now this little helper has a list of all the eigenstates of the observable. So he's going to pick, if I got m, he's going to grab state with label m and output it. That takes a little time. And then there I am with my state, with my ordinary quantum mechanical post-measurement state. So that's quite neat. And yeah, okay. So here's a little list for the last few minutes of what we really learned from this finger exercise. We do know this in a sense already, that the projection postulate in a sense protects the identity of an unknown state because it destroys it effectively if you perform a measurement. It also necessitates proper mixtures because if we take away the projection, we don't need proper mixtures anymore, so that has to be directly related. The projection postulate will also create these quantum correlations, leading to local tomography, for example. That's the next item. And it enables some quantum information protocols, because there were some which I couldn't do, because the collapse, if I measure here, things don't collapse over there. So that's what the projection enables, and it complicates others. The extraction of the state after a quantum circuit is much harder to come by. That's related to the protection up there. It limits, in fact, the computational power of ordinary quantum mechanics. Normally, we think of quantum theory, quantum information, improving the computational power, but that's compared to classical mechanics. And then the projection is, in fact, essential for the perennial question of the ontological status of the quantum mechanical state. Because if we change our update rule to a passive one, we just deal with an object which we can handle and look at and identify. Okay, one last step up in order to actually create the link to the reconstruction programs, which is the main topic of this conference. I can quickly generalize what we had before by just now talking about density matrices instead of pure states. So that's a bit more advanced as a theory, but other than that, not much changes. The expressions for the probabilities change. But now I imagine that I can, of course, think of many other update rules, right? I don't have to use the Lüders rule for quantum mechanics or the passive rule, but I could use anything really if I wanted and see what happens. So that's the idea of an alternative measurement theory, the AMT. If I perform a measurement of M, my state rho goes into a rho prime. Here's the update rule, A for AMT, which depends on the measurement, the observable, the outcome, and the state I had in the beginning. And now I can start to look at what are actually reasonable update rules. Do they have to satisfy certain properties? That's then a little bit tricky, and I don't want to go into that. But so we have seen here three cases. The Lüders rule is the first one, which is the one we know, the update rule for density matrices. This is the one for passive quantum theory. And then there could be a general one. And of course, there are within immediate reach some generalizations. You can just mix the Lüders rule and the passive rule by saying that with a certain probability, the state will update according to the quantum mechanical rule, or it will stay as it is. And I can sort of connect these two cases just by a convex combination. And the interesting thing is when Q is 0, I have the quantum mechanical case. And as soon as I turn on this little Q and make it a little bit positive, the ontology, in fact, changes completely of the states of the theory. Because as soon the other way around. If I am at the passive end, if Q is 1, and I have a classical ontology for the state, and then if I add in a little bit of the quantum part, it sort of immediately flips over. Unfortunately, it's not sort of continuous. But this update rule here, in a sense, means, if you think about it, that you don't get a complete collapse onto the eigenvalue M, but you get sort of a preference for M, and the rest can be sort of the same. So there's lots of things you can explore. In particular, you want to classify all your update rules, and you want them to be non-signaling, for example. You want them to be well-defined on composite systems, and that's something you have to write up carefully, but I don't want to bother you with that. So here's the link to the reconstruction idea. I haven't seen attempts to derive the projection postulate except in von Neumann's book, where he introduces it, and is heavily based on quantum experiments, cloud chamber observations by Compton and someone else. And so there's some scope you can work on. Are there any physical principles? Can I single out physical principles which would tell me that the Lüders update rule is a good one, which I should use, and which excludes all the others? And so I want to have a physical principle, or more than one, which tell me on intuitive grounds why the Lüders update is actually the one which nature has chosen. I can't give you an answer to that, unfortunately. Okay, summary. I said most of these things a number of times. So we have a consistent no signaling, computationally powerful foil theory of quantum mechanics. The p states are observable. There are various properties I mentioned before. Here's an interesting point. You might know this nice paper by Mermin, where he introduces the Ithaca interpretation of quantum mechanics, where he says what he would like from an interpretation. And passive quantum theory, funnily enough, ticks almost all the boxes, right? There are some things where it's not exactly clear whether it's okay or not, but it's quite surprising to see the set of properties which Mermin lists to fit nicely what Mermin imagines would be a wonderful interpretation of quantum theory. Not all of them work, but okay. And the final thing is that I presented you with a framework which gives some work for reconstructionists to do in order to single out the projection postulate of quantum mechanics. Okay, thank you for your attention.
Thanks so much, Mike.
Thanks. I'm just a little confused, and I'm sure it's just something I misunderstood. But on a couple of slides ago, you said, so there, next one. So the quantum mechanical projection postulate is essential for the ontological status of quantum states. But I thought earlier you said that PQT has a nice, clean ontological interpretation. Could you clarify how those two statements are connected?
Here's a list of things which the quantum mechanical projection induces. So if I go from PQT, where I have a nice ontology, and I change the passive update rule into the ordinary Lüders rule, this classical ontology just goes away. So it must have to do to some extent.
Oh, okay.
You see?
Okay, I see what you mean. Okay.
Okay.
Yeah, this is really a beautiful toy theory to play with. And I'm just going to go back to the same issue that Mike brought up, but maybe to make it dramatic for our organizers. Do you know the Tolkien character Wormtongue in Lord of the Rings? Well, there's a colleague of ours in Vienna who whispered into the organizer's ear that perhaps cubism is empirically not falsifiable. And so I'm always seeking examples so that when someone says that nonsense, I can hold up an example and say, this would invalidate cubism. No one would dare make a cubist interpretation. And this is just a beautiful example of, cubism couldn't go here because your quantum states automatically become ontic through this modification of the rule. So that's really cool. One comment about the generalizations of Lüders' rule. And maybe somebody else in the audience can comment more, but there's a little book by Jeffrey Boob where he tries to give a justification of Lüders' rule as being the closest analog that one can have to Bayesian updating. And this was long before he was thinking of quantum states in Bayesian ways. This was in early 80s. Okay. That's at least one way.
Well, this update rule is the closest you can get to a classical update rule.
Yeah, I think that's. Yeah. Oh, I see. Classical Bayes rule is what he showed.
Thank you.
As close as possible.
Lucy.
The first of the update rule, the thing that came to my mind immediately is that there are, of course, a lot of update rules which are standard in quantum mechanics beyond the Lüders rule, essentially equivalent. So when the when you have a POVM, and the update rule takes the form of basically a Krauss decomposition. So there's a well-known set of update rules which are standard in quantum mechanics anyway.
Yes, but you can all boil them down to the projection.
That's what I'm saying is equivalent in some sense, but
yeah.
they would formally, of course,
much
sure,
but
larger set.
From a fundamental point of view, they are not independent.
Hi, thanks. It was really interesting. I wanted to kind of ask things related to Mike's question, to ask a bit more about the kind of, you said there's a classical ontology that comes out of this, updating this projection postulate, and I wasn't quite sure what you meant by the classical ontology, beyond the idea that you can determine the state in its entirety through repeated measurement. But like, are we, because it seems that you still got kind of a wave ontology, or?
No, well, it's just an object, the properties of which I can completely determine by my measurements. I think of it as it's like a classical ball.
Even though they're still probabilistic?
Interestingly, if you perform measurements on it, you get probabilistic outcomes. Yes, that's true. So the ontology in that case, to know that you can extract which state you're talking about, is not logically connected to the fact that this thing might respond probabilistically to you. Right? That's what we learn from this. It separates out these two aspects. Is that sort of an answer?
John?
Yeah, thanks. I really liked that. I was basically going to say something similar to what Rudiger said, and also just ask why you didn't consider anything other than unitary evolution in your generalizations. But now I think I can see that it's because you've baked in Church of Larger Hilbert space, basically, so you're just going that way.
Yeah.
I'm a little confused by repeated measurements, because if instead of repeated strong measurements, if I imagine a situation where we let the system evolve for a little interval of time, then measure it, evolve, measure, if we do such a sequence, and then also make the measurements to be weak measurements, in standard quantum theory, we might expect the state to undergo some stochastic time evolution, but it seems here we have a deterministic evolution, even in that situation. Won't that lead to a difference in the predictions?
Well, yes. I think that the predictions of this theory, some of them concerning time evolution, no, they are actually still the same.
Yeah.
But I can extract the probabilities in different ways because I don't need an ensemble to calculate my probabilities. I need only a single copy is sufficient if I can sort of freeze it and then measure on it.
Even for a single copy, if we just let it evolve and then do sequential measurements after an equal interval?
You get a random sequence of your measurement outcomes if you measure some observable like M. But the state just does what it does under unitary time evolution. And I haven't thought about what this means in the context of weak measurements. I don't really know.
Okay.
Thank you.
Yeah, thanks very much for the nice talk. I mean, the fact that you somehow need a collapse, for example, for an informational interpretation of the state, that's something that holds also much more generally also in any probabilistic theory where the state is just a set of probabilities and you allow the observer to change their state of information, and basically the collapse is essential. But now actually another comment I wanted to make is, are you aware of this derivation of the Ludas rule from a maximum entropy principle?
No, I haven't found that one.
Yeah. So it's or maximum relative entropy between the pre-measurement state and basically the post-measurement.
Who did this?
This is Richard Kostecki.
Okay, maybe you can give me the reference. Yeah, because we've been trying to find exactly this type of thing, but we haven't, and I'm very grateful if you can tell me.
Yeah.
Okay, so, yeah, Rüdiger.
So I have some doubt on whether the Lüders rule is really equivalent to this set of larger, so the Krauss operator rules you could have, and this in the context of the repeatability, because I mean, from my perspective, I do not regard the Lüders rule as special, as a special one. They are all these various Krauss operator rules are similarly good.
Yeah, but you can actually.
Wait. Sorry.
Yeah.
What this means, though, is that if you repeat measurements immediately, you have no longer guarantee, or there's no principle that says that you need to get the same outcome, because the Lüders rule is no longer singled out as the one sort of fundamental one that really happens or so. And I don't think the larger Hilbert space in that case helps you. So you would basically lose that. So there's a real difference between why the Lüders rule is fundamental or as regarding all of them as.
If I recall correctly, if you take the Lüders rule, you can compose it, put it together with an arbitrary channel. And then the Lüders rule plus this channel is good enough to create all possible linear update rules you want. But I can imagine nonlinear update rules as well.
Oh yeah, of course. Yeah.
So there are many more.
Yes, no, your project of characterizing this, of course, is unaffected. I was just commenting on the immediate repeatability, which distinguishes the Lüders rule, treating it as special from treating all the quantum mechanical rules as similarly fundamental.
Yeah. Okay. Thank you. Yeah.
Okay, so let's thank again our speaker.